Learning Outcome 9.3. Describe how the unilateral and bilateral Laplace transforms are related. In the videos for Learning Outcome 9.1 and 9.2, we introduced the analysis integral for the bilateral Laplace transform. It is shown again here. It's the integral from minus infinity to infinity, x to t, e to the minus st dt. The unilateral Laplace transform has a very similar analysis integral. We use a script x instead of a regular playing x to denote that we've got the transform as a unilateral Laplace transform. But both of them are capital X's. And for the unilateral Laplace transform, the analysis integral has limits of integration from time 0 to infinity instead of time negative infinity to infinity. The remainder of the integral is identical. These two transforms are very similar. So let's try doing a calculation with both the bilateral and the unilateral Laplace transform for a signal x of t equals e to the minus at u of t. This is a signal which is very commonly used in signals and systems. I'm sure you've used it before. For the bilateral Laplace transform, we start with our analysis integral. We substitute in for our x of t. We note that where the u of t is, it just changes our limits of integration, and the u of t gets replaced by a 1. We're going to pause here and go to the unilateral Laplace transform. Notice the script x, which is defined to be the integral from 0 to infinity of our x of t, e to the minus st. Make our substitution. Because our limits of integration already are from 0 to infinity, the u of t just goes away, just becomes a 1. And at this point, our bilateral Laplace transform and our unilateral Laplace transform are identical. For all the problems which have a u of t in them, bilateral and unilateral will be the same. Because they are the same, and most problems we work with in signals and systems have this u of t, have our problem starting at time 0, quite often it's not mentioned to you whether you're using a bilateral or unilateral Laplace transform, because the net result is the same. In your book, you've got table 9.1 and 9.3, which show properties of the unilateral and of the bilateral Laplace transform. They're very similar. Both start with linearity. Both show your signal, your Laplace transform. But you have a region of convergence when you're talking about the bilateral Laplace transform, which is not in the unilateral Laplace transform table. Also note differentiation in time. This is something you used quite a bit when you were using Laplace transforms in your differential equations class and your circuits class, because you were using the Laplace transform to make it easier to solve the differential equation. So if you look at the differentiation in the time domain for the bilateral, you have your derivative operation, which gives you a transform of Sx of s. And for your unilateral, the derivative gives you again your Sx of s, but now you have this initial condition. We did not have that in the bilateral because the initial time for bilateral is at negative infinity when nothing's happening. You saw this all the time in your differential equations class and your circuits class, and they didn't tell you why you were using that, and that's why it's not here. Another thing to note is that in the bilateral Laplace transform, there is a time-shifting operation similar to what we saw in the Fourier transform, and for Fourier series, and for discrete Fourier transforms in Chapter 5. This is not in the unilateral Laplace transform, because with the unilateral Laplace transform, we have that fixed boundary of time 0. If we were to pass that boundary, suddenly things would be changing. So we don't have that in the unilateral Laplace transform. Those are the biggest differences between the two. In this course, we're just going to work with the bilateral Laplace transform. You know you've already used the unilateral. You should continue to use the unilateral for those other applications. But now you know more.